freue mich sehr, dass ich heute die Gelegenheit habe, das Thema Entfluchtungssimulation.
It is a great pleasure to me to be able to present on evacuation simulation to you. Thank you very much for having come here, everybody. Thank you very much for listening to me. And feel free to pick up a printed copy of my presentation in the rear. You will get it for free, provided that you fill in a questionnaire. On the left, we can see something. Yes, this will take another minute, but maybe... Let me tell you in advance that this is not the first slide. Do you want me to push the button or shouldn't I? Okay, so this is the title slide. We don't have to look into that. Evacuation has three different terms in German, but actually they basically mean the same. It's all about evacuation, whether we use the terms Entfluchtung or Räumung or Evakuierung. Here you can see 7 items that I am going to just go through. I'm going to talk about computation and simulation processes, but I would also like to embed these in a wider context. And this is why I'm going to start at the beginning with motivation and human action. I am then going to talk about the movement of an individual person, and I'm talking about the movement of many people as we have them in major events. I am then going to talk about visitor management and control, as well as different computation and simulation processes. I am going to focus on pedestrian traffic at events, in the environment of events, and in public traffic, and then I'm going to talk about evacuation. Let me point out that this table of contents is widely dealt with in a book that is to be published in May. So actually this presentation is strongly based on this book, which I wrote together with 2 colleagues of mine. Starting points. Well, some of you may have listened to other presentations today, or they will listen to some more presentations. So many of the things I am going to touch upon have been covered in part and from other points of view by other speakers here. Authorities, accidents, as shown by Mr. Rolfes, risk assessment, evacuation tests, and trade fair safety. I am going to briefly skip through these points because actually they have been covered by other presentations, and I would actually like to narrow down my focus on what I am an expert in. I am not an expert in these previously mentioned fields, but I am an expert in simulating the flow of people and simulating their evacuation. When it comes to motivation, we have to think about several sub-aspects: needs and goals, safety, well-being and comfort, and collective behavior and action. This is a rather complex graph. What is decisive here, from my point of view, is that human movement and human action in general are nourished by needs. And the underlying thesis is, formulated by psychology experts, that human beings have several general needs in common, needs that everybody has, and you want to satisfy your needs. So what is the motivation to attend a major event? The motivation may be that it is fun. And the second aspect is that you need to have control and orientation, which you basically need whenever there is a stressful situation, whenever there are constraints or problems. These needs must both be met, and the focus may actually change. Fun orientation may be replaced by control or rescue orientation, depending on whether you are in a stress-free or in a stressed environment. And then there are some more aspects. So the few points that I just mentioned do not account for everything, but they are the underlying motivation. Now, if we open this up a little further, we can take a look at factors having an impact on the well-being and safety of human beings. Many of them can be controlled by technical means. Heights, for instance, and fluctuations in position, they might play a role. Vibrations, noise level, ventilation, the composition of air, such as its CO2 content. And in the next part of the pie chart, we are looking into the level of occupancy. How many people are located on 1 square meter? Maybe 1 person, or 4, or even 6. And the dark gray area in the outer circle is the level of discomfort. This is where it becomes uncomfortable. So one parameter to determine safety and comfort, a parameter that is relatively easy to capture when it comes to controlling and steering movement, is the level of service. The number of people in a defined area. This has to do with quality levels. It has to do with road traffic planning. This is where it comes from originally. And if you calculate it the other way around, you may as well calculate how much of a surface, how many square meters are available for an individual person. And then there are the sources of experience and behavior. I had mentioned the needs of people. In motivational psychology, you will encounter motives such as performance, power, and affectation or links with other people. But sometimes we also have to deal with habits, with temperament, with the heat of the moment. Sometimes people behave differently if highly emotionalized. And you also have to look into stress coping capabilities. The ability to cope with stress will be decisive in determining whether there should be top-down control by means of cognitive processes, by means of thinking, by means of just doing what you want. But if the stress is overwhelming, if you can no longer cope with stress, it will typically be controlled bottom-up. In such a situation, the heat of the moment and habits will govern the situation. And this actually explains why rescue forces train their deployment and action situations on a regular basis under real-life conditions in order to develop habits for the case of need. So firemen, for instance, have to get used to the heat. Heat has to become a matter of habit. And if we look at the stress coping point, the change from top-down to bottom-up, or the other way around, does have a massive impact. Very often, the behavior of visitors changes dramatically in stressful situations. If we want to capture all this quantitatively, when it comes to dimensioning exits, emergency egress facilities, etc., you really have to think about the motivation. People decide in favor of specific goals. They say what they want to achieve. For instance, if I come to this trade fair, I typically use the train, I get off at the train station, and then I follow the signs. And the event plaza is shown by signs, so I will find my way there easily. And this is how my plan was fulfilled without any problems. But if signage is incomplete, if in the meantime I no longer know where I am, if I have to find somebody to tell me where to go and what route to take, this really throws me out of my habit. I have to start reorienting, and I'm really out of my routine. When it comes to collective behavior, well, in the fields that I am going to deal with today, we are in small spaces and we spend just a few hours there. So from a sociologist's point of view, there are, of course, things going on at a much larger scale. But if we break this down to this small scale, individual behavior and collective behavior sequences, this deals with how people behave in the audience. For instance, everybody's still here. A predictor for whether people will stay here is whether the presentation will be interesting, etc. So you really have to be able to predict human behavior. So now my presentation is going to be more application-oriented, more practical. I've been talking theoretically about human motivating factors. Now let me talk about the movement of people. Movement to an event, movement during an event, movement away from an event, either in a regular situation or in the context of an emergency evacuation. Let's look into anthropometrics, measuring people. How tall are they? How wide are they? How heavy are they? Due to the demographic change and development, there have been some changes here, and then there are some physical basics that will always apply. If, for instance, you stand on a sloping surface, if the slope is too steep, you can no longer stand upright without any handrail or support. And if people keep bumping into you, the likelihood of stumbling and falling increases. Next, people have different space requirements depending on their special needs, depending on the surface structure, depending on the lighting of the environment. And if you are disabled in any way, for instance, if you are a wheelchair user, you need more space than an individual that has no special needs and will just stand up like this, like you see in the top left corner. This does, of course, not apply for people moving about with a child in a pram, for wheelchair users, or for people moving in groups. I am going to present you with some ISO standards going by geometry, population, the environment surrounding people, and the level of hazard or risk. Whenever there is a dangerous situation, space requirements are different. Next, you have to look into the speed of movement. In big cities, pedestrians typically walk faster than they do in rural area. In leisure time, they walk more slowly than while at work. When they are tourists, they walk more slowly than when they go shopping, etc. And then, of course, the walking speed depends on age. It starts at an age of between 1 or 2, and then you arrive at a maximum when you're about 20, and then it remains at a fairly constant level, and from 60 years onwards, the slope goes down again. When thinking of the average population, of course, you have to come up with an average curve or characteristic, and this characteristic does not necessarily apply to every individual. Now let's look at the situation of many people being together in one place. Walking speed is different when you're by yourself or when you're walking in a crowd. The denser the crowd, the lower the walking speed. If, for instance, you ask the question, how many people can walk through this door or can walk through this aisle, there will be a maximum or peak value achieved at a medium level of density here. Think of the flow of people per meter and second. In the US, of course, it would be measured in foot rather than meters. We see a constant increase in line with the width of a door or pathway. The specific flow of people, as empirically calculated, is quite constant. We see relatively high levels here. We can see 2 people per second at this point. And what this means is that the assumption of the 60-centimeter module in the ordinance governing places of assembly does not always hold true empirically. And actually, this has been taken up in the draft of the revised ordinance. As far as I understand the draft, a linear interpolation will at some point be possible. And this is due to the fact that the constant flow has been taken into consideration. Here you can see speed declining with occupancy density. What I cannot fully understand here is why the speed is supposed to go down even at a low level of density, a low level of occupancy. If you are way below 1, well, there is still enough space for everybody to walk freely and in an unhampered fashion. This is the Fire Protection Engineering Manual from the US for evacuation simulations and calculations. In this book you see the parable with its opening toward the bottom. You can see that the curve ends at 5.4. Predijinsky and Malinsky in Russia measured values of up to 10. And this leads to problems, because you may ask yourselves now, which manual, which simulation am I going to adhere to in my own situation? Well, I'm not going to give you the answer to that. I would just advise to keep an eye on the variety of possible outcomes. And then you have to look at the crowd of people in the right way. For instance, if you look at them from a balcony, but you look at the crowd in a diagonal fashion, you will not be able to determine the density of people. So you'd better go by warning signals, such as congestion phenomena, or the flow of people coming to a halt, or stop-and-go waves, or lateral movements of the crowd. And this makes sense once you put it into a relationship with the preparations, with the scenario that you have developed. You have to come up in advance with a solution for a situation of panic or even a lower level of problems, such as a halting of the crowd. When it comes to panic, I've discussed this quite often, and we can discuss it in greater detail later on if you're interested, but I would like to focus on my thesis here. I don't think that panic is something that comes out of the blue and then it creates a huge situation of trouble. No, panic is what is generated by a dangerous situation, by a problem that is there first. It's not the panic that is the problem, it is the underlying situation that is the problem.
So I basically came up with the three phases. First is preparation, planning, and risk assessment. Then it's organization, measures, supervision, communication. And the third is actually follow-up, which is an evaluation documentation. And what I would like to do now is to point out to a couple of different papers that were actually already delivered, and then you get into a lot of detail. It's a lot about risk assessment. It's whatever you want to call it, but it's really about preparation, and then basically you touch upon a couple of issues. It's like basically it is all about security services being in place, and everything has to come together. And I also think that that would go beyond the scope of my paper, so I really want to focus on evacuation simulation, but I do consider this to be extremely important, and I even think that that is the most important issue, and therefore I think also it is very much up to the event managers, the event management team, obviously in cooperation with the security officers and also with the securities, making sure that everything is happening peacefully. So that much on the calculation measures, and obviously that is also everything I wanted to say about the application. So simulations is also what I would like to mention. So that is just a rule of thumb, and I consider this to be extremely difficult. We already talked about that, about the flow of people. So if you just want to take a look at the flow of people, let's assume there is an assembly venue, and then basically you have the limits defined by the width that is limited, and then you can actually assume there's a constant flow rate. So that is 1 person per square meter in second. And that is basically a very good rule of thumb, and then you can calculate how long it's going to take to evacuate that room. Obviously, provided everything works out quickly. So let's assume you have 200 people. I just have to make sure I get this right. 200 people. It's 120. I hope I can do the calculations right. So that is basically according to the Act on Venues for assemblies. Now, I'll start differently. Let's assume you have 1 person per meter per second. Then you have the 200 people that actually come into the location through the door, which is 1.2 meters wide. And then I think how long it's going to take? 80 seconds or something like that. Yeah, 200 divided by 1.2, that is a minute and a half for the flow time. You know, people have to get up and all that. But what you basically see is that gives you a minimum threshold. So it's a minimum of 90 seconds, and it's then going to be the correct value if everybody's basically following you straight away. And that is what I'm trying to say. Obviously, it also depends on a couple of other issues. You know, how long do people have to walk and all that kind of thing. So there's a lot of restrictions. So simplified procedures will only be helpful if it's really going to be about very simple structures. Obviously, if things turned out to be more complicated, more complex, people don't react straight away. You have different flows of people that come together. And then in those cases, obviously, that very simplified approach is not going to take you very far. Yes. Oh, I did make a mistake. I did make a mistake in the calculation. I think it should be 160 seconds. Yes, so I did actually not do it right, so I'm sorry for that, but nevertheless, you can still actually do your own calculations, and then there's still some transfer of knowledge going on in this hall. So that much on that. So let's talk about the more complex procedures on simulation. That is one example that I brought here that actually comes from a ship, a passenger cruise ship. So we do a lot of work for them, so there's uniform international standards for them. It's not only true for all ships in Germany. You know, Germany is still a very strong shipbuilding nation, so that would also be true, you know, if ships were made in the US, which obviously is not what is happening, but they would actually be cruising in the US. So, and that is the marine navigation system. So you have these kind of rescue steps. You can see different routes for the passengers. Obviously, they would need to be taken to boats. So blue is the crew, and green would actually be the passenger flows. And what is that actually showing you? That is basically how simulations would work. So everybody would actually start going towards the escape route at the same time, and then there would also be a mix-up. You can actually see red, green, and yellow dots on the chart. The green dots, that is people that actually have their free speed, and the yellow are in between, and the red ones are obviously stuck in a traffic jam. What you can actually see, that is the agents, I call them, that is basically the people in the simulation. So they are green, so they would actually go to the way, to the escape route, and then to the point where they could embark on the escape boats. And then there's another one where the crew actually waits until the passengers have left the boat. That is exactly the same thing that is happening here. So that is just an example that we basically created in our own facilities, and you can basically neglect technical details. Obviously, I can actually share some knowledge on that. You can also check our website for that kind of information, but I would not want to touch upon that here. So this is just going to show you what that kind of simulation would actually be like. You could then also define, okay, there's different groups of people. When would they start moving towards that escape route? So what kind of features would that people have, and all that kind of thing. And you can do that with very, very complex calculation measures. So you basically have a span that you covered. So that actually covered the whole range from a very simplified approach to the very complex situation. Obviously, there's different simulations and processes in place between that, but I can't really touch upon that now. So really, it is about that strategy now, which makes it much faster. You can't see that just looking at the picture. You just would need to compare a couple of things, but that would actually be 3 minutes faster. So if you just confirm it or transfer it to percentage point, it would be 30% faster if you just assume that as 10 minutes. And you can basically see that that is a very simplified illustration, and also these shapes and stuff, you might actually overtake people. So these kind of animations can actually be used in order to discuss issues also for a more heterogeneous group. We already talked about the importance of communication this morning. So if you meet people in a larger group, that is the firefighters, that is fire prevention officers, there's the supervisory building authorities present there. So that actually helps you a lot to bring everybody around one table and to really focus on the issue at hand. So let's talk about traffic. I have already mentioned that you could actually do that kind of thing to evacuate people. I'll show you an example for that straight away. But you could also use that kind of approach for traffic controls and monitoring. In this case, obviously, I refer to pedestrian movements. So that is just a very, very short illustration of a chart, and I just want to take you through what are the steps that are relevant for the planning process. So obviously I'm here quite a lot at this fair, so obviously you would need to adapt a couple of things, and then obviously you would not need to go through all the steps. If you see this kind of thing, then obviously you see the simulations, the calculations that were involved, and that actually helps you to analyze things and to predict future scenarios. And then you obviously have to check that for them actually coming true. So have you made the right assumptions, or do you need to reevaluate a couple of assumptions that you made before you then actually go into the realization process? So what I'm trying to show you is basically that it is only about the design phase quite at the end of the process. That is actually changing now. Slowly but surely, we started with these kinds of simulations in the late 1990s, also because there were a couple of activities after the Estonia went down. There was 1994, 1995, obviously it was done for cruise ships, and basically people started to do that very, very late. But now actually they developed that kind of thing already for ships very early on in the production process and design process, and then you can still change things. It's different for buildings because when it comes to buildings, usually we're involved very, very late on in the process, usually when everything is almost up, and in some cases we're only involved after problems already occurred, and therefore I think it's always better to do it right from the beginning. But it's, you know, it's the same like for everything, and it's an experience we've made over and over again. So therefore I'd really like to be involved much earlier on, so that we are not actually taking a look at already set up buildings, but that we'd actually be involved much earlier on. But that is just a wish that I'd have. So what I've been showing you in terms of examples were really minor details. If you take a look at the larger picture, then you could actually see access roads, you know, for an event. So you can see a station here. So obviously trains would be arriving here, people would walk over here, and then they would basically come up to the fair area here. Obviously, we used some different simulations that was developed at the University of Technology in Berlin, and they basically designed that for large-scale dimensions, and it's not about dots, it's all more done with the help of bars. It's really on the basis of roads. And what's quite interesting that you can actually track things like train schedules. You can also consider processes that take a couple of hours, you know, where would people be, where might traffic jams occur, and then basically it is about bringing the smaller elements into the larger picture. And there's also the crossroads here, and obviously all these issues could actually be viewed like through a microscope. And a couple of things that actually always hold true that can also be reflected in simulations. It very much depends on the focal point of your research, but I mentioned already the traffic jam waves, you know, the stop and go, what is happening if you have movements coming towards you, and then also you have the traffic jam wave. So that might actually be familiar for a lot of people that deal with that kind of thing already for quite some time, and that is something that most of us will be quite familiar with. So let's turn to the last section, to the last part of my presentation, and let's talk about the evacuation or evacuation simulations. Let's talk about that kind of thing. So maybe to start with, I'd like to define the term I use, emptying or evacuation. That usually is what the firefighters are working for, spontaneous actions. And evacuation is usually the term they use if there's a bomb threat, if there is weapons and weapon threats, and if you plan to remove people for a longer period of time, if you plan to take them out of a certain area and taking them elsewhere. So when the firefighters talk about an evacuation, then that comes also with tents being put up, would be putting people into gyms and that kind of thing. But if there's a fire in here, and if there's an alarm going off, if there's an announcement that's only about emptying the building, getting out of the building, and nobody needs to worry about some hot tea being served outside. So obviously it is also about protection goods and protection targets. That is basically bridging back to the beginning of my presentation. Most of all, it is about the legal motivation, then it is about the further items on the agenda. It's really about the emptying phases and also obviously design results. And I'll come back to something that I've already mentioned. I'll also take a look at the evidence that is available. So let's talk about the protection goods and protection targets. That is very important. It's also part of the Federal State Acts on building. It is really about the protection of life and health of human beings and animals. So that is all those issues that are also part of our legal structure in our state. And again, obviously, as I said, it's about life and limb, about life and health. It's also about public safety. It is about property. It is really about firefighting by the firefighters. So that is very, very important. Obviously, these two issues are usually separated. On the one hand, you would like to see people getting safe by themselves and be safe when the firefighters come in. But on the other hand, obviously, you also want to protect property and somebody else's property, and that obviously is fighting the fire. But that somehow implies that you get the people out quickly first. So these might not be originary targets of the organizers, of the operator. Don't get me wrong, but I'd like to phrase my sentence. So the focus when it is about the organization and planning of events is definitely not about the dimensioning of escape routes. Obviously, it is about having satisfied visitors and having a smooth operation, but obviously it is a lot about other issues, and obviously it is very much about economic pressures that you find yourselves in. So obviously that creates some tension, and obviously then there's different people that work on these issues, obviously representing different interests. So what kind of evacuation phases or emptying phases do we know? I actually mentioned the 4 phases. And again, it links back to what I've presented in general. So obviously you simulate the 3rd and the 4th phase. That is really the reaction and the movement. The situation of detecting a fire and then making an announcement and ringing the alarm, that is something that is not being simulated. But when you talk about the time it takes to evacuate people and to move people, then obviously you would need to add the time that is needed for the fire detectors to detect the fire and to announce that risk to visitors. And that time that you then arrive at basically gives you a kind of bigger picture. So if you do something like a risk analysis, then obviously you need to take into account the time you need plus an available period of time. So if you basically refer to protection targets, so you want to make sure that you know that people are safe, and then you also want to know when does it start to get dangerous. Usually it is the smoke from fire that is dangerous in facilities, or if basically the coating comes down to a certain level. And obviously there is also calculation models to calculate that kind of point, but obviously that is also the values and numbers we are given. That is again something from the guideline of VFDB that, for instance, is a lecture hall. I've already mentioned that there's not only simple calculations, but also complicated and complex calculationary measures. So you can see that on the right-hand side, so that symmetry is being divided into escape routes, into escape route elements, and then you do the calculations for that. You calculate for flows, for capacities, passenger numbers, and times you need. And obviously, if you want to do that for a whole fair, then obviously that generates a lot of paper. So it's not only about not arriving at different results, but it just makes it all the more harder to basically refer back to that. So simulations again. What is a simulation? That means there's a lot of simplifications. So obviously that goes without saying in a certain way, but obviously that is easily understood. But nevertheless, a lot of people forget that people are called agents. The assumptions you make are being fed into parameters. So obviously the simulation result can basically be done away with if response time is not being accounted for. That is also something that you could do. It's like somebody is drunk in a toilet, and obviously they don't notice that there is an evacuation action going on, but that is then not very helpful, that kind of detail, because obviously you can't really account for that kind of thing in your calculation. There's assumptions, there's also interpretations, and obviously then you document these findings, and then that is to make things easier. In the end, obviously, again, the results are being documented, interpreted, and in the end, you basically come up with some acceptance criteria. So that is not something that we have in event management. Usually there we talk about length and width. So what we usually do, we simulate, for instance, a certain situation that could actually easily be approved. And then if we have a deviating situation, then we compare these two. And then we actually say, okay, the supervisory building authorities or the firefighter departments might actually say, okay, that is still within the limits of something that we would have expected and accepted elsewhere, or is that not so? And then again, if that is a kind of lecture hall that we compare that, so obviously everybody would be leaving immediately. And that actually is based on the Act on Assembly Venues. So I can't really say, but I think it's 1,000 people, so that would actually mean that is 6 meters, and that is basically what you'd have. And then usually it takes 7 minutes based on that simulation. Don't nail me down to details, please, but basically it is retrievable, so we have some very detailed findings on that. So can I go back? I just wanted to show you the right-hand side here. So this is what you can see with escape route 2 to the front. I have to be careful with what I'm saying because the sum of escape route width basically is probably true for the 2 escape routes, so therefore the 7 minutes. So I have to look that up again. Sorry about that. So what I have already mentioned as well is all the different assumptions that also concern people. So this way of simulating things is true also for senior people's homes or nursing homes, and it's quite similar with other factors that you could actually think of. So let's think about cruise ships. So you have to account for the movement of ships. So if you have this kind of rolling movement and the amplitude is something like 15 degrees, then hardly anybody is moving anymore. So some people might actually get sick, and some people might not be able to basically know where they're going. So orientation is very difficult. So, and that might actually be used a lot also in forensic issues. So if you want to understand things later on, then that might be very helpful. So we call that egress now, that is the standard evacuation. So very often we are dealing with that kind of situation. In that lower part, obviously you have to also account for complex situations, but we usually assume that they have proper illumination and proper signage. And sometimes obviously you can make it all more complicated and more complex and also more inconvenient, and nevertheless then you'll arrive at different results, and obviously you have to assume that the roads are not blocked and that the people can understand the announcements being made and all that. So you already probably will know that I'm saying a lot. You've got to be cautious, you've got to have in mind and that kind of thing. And this idea is basically summarize what I'm trying to say. So everybody needs to be interpreted. So it's not really about people that are moving these little dots, but people are here in the room. And obviously we're much more complex than what I've shown you here. But nevertheless, the models are very helpful and very useful because provided you have very clear assumptions, you can basically deduct findings that are firstly very, very important, and that secondly can also generate a lot of good. So thank you very much for listening to me. I hope you enjoyed the presentation. Thank you very much for your attention.